We found in the last video that the volume underneath a surface is given by the limit of this particular double sum, where the upper bound of the first sum m gives the number of subintervals in the x-axis, and the upper bound in the second sum n gives the number of subintervals in the y-axis. And we called it as the double integral over the region R of the function f of x times the differential element of the area, which is called dA. And because we are calling this as the double integral, in a sense we have defined the double integral over the region R of the function f of x with respect to the differential, with respect to this area, is the limit where both m and n go to infinity of this double sum. Now we will do a problem. The problem reads as follows. Estimate the volume using midpoint rule below the elliptic paraboloid z equals to 16 minus x squared minus 2y squared onto the region R equals to x interval starting from 0 and ending at 2, along with y interval starting from y equal to 0 and ending at 2. Divide the x interval into 2 equal subintervals and the y interval into 2 equal subintervals. The first thing we should do is have an idea on what the region R looks like. Okay? So we know that x varies from 0 to 2. Similarly, y varies from 0 to 2. That means that R must be this rectangular region over here. So this entire rectangle is actually R. Now we will focus on x-axis. The x interval starts from x equal to 0. So the first point is a equal to 0. Similarly, the x interval ends at 2, so b equals to 2. And the number of divisions we will have is given in the question as 2 equal subintervals. Right? So we will have m equals to 2. That means delta x equals to b minus a divided by m. b is 2, a is 0, m is 2. This means this must be equal to 1. Similarly, we will find the endpoints for the y-axis. The y interval starts from 0 and ends at 2 because of this. And the number of subintervals that we have along the y interval is also 2, as the question states. That means that the length of each segment along y-axis should be 2 minus 0 d minus c, and n equals to 2. This is also 1. I will find the area of a small segment, which is in the last video we have seen that the area delta a is delta x times delta y. That means this is delta x is 1 here and delta y is 1. So this is also 1. Now we want to draw the grades that we will need. Right, this is our region R. Now x starts from 0 and moves 1 unit by delta x, right? By delta x. Delta x is just 1, that means we start from 0 and then we increase by 1. This should be at 1. Now we need to draw a vertical line on x equals to 1 so that we can make the grade. Now again from x equals to 1 we move by 1 units to delta x, which is just 1. That means we end up at 2 now. Now at 2 our interval ends, so we don't have to do anything. Similarly, now we will move our focus to y-axis. We start from y equal to 0 and move up by 1 units because delta y is just 1. So move up by delta y at y equals to 1. And here we will have a horizontal line and then we will, as we are at y equals to 1, we will start from y equals to 1, move up by again delta y units, which is 1. So we are at 2 now, but our interval ends at 2, so we don't have to do anything. This is actually our grade. there are only 4 rectangular area where each of them have an area of delta A. What we need to do now is find the midpoints each of these rectangles. Let me get this out. So the first one is in between, the x coordinate is in between 0 and 1. That means you can work it out with a formula if you want, that a 0 plus 1 divided by 2 is half, or you can just see from the diagram that it must be x equals to half. And the y coordinate is also from is within 0 and 1. That means it also must be half. You can work it out with a formula if you want, which is just 1 plus 0 divided by 2. And similarly, we can find the other midpoints as well. Here it's the x coordinate is 3 by 2. And the y coordinate is still the same, which is half. Now this midpoint has the same x coordinate as this one, which or here, which is just half. To work out this midpoint, you can just you can just sum 2 with 1, which is 3, and divided by 2, so we get 3 by 2. Similarly, in this midpoint, we are in between 1 and 2. So the midpoint in between 1 and 2 is 3 by 2. And the y coordinate is the same as this one, which is also 3 by 2. Now let's find the volume under Z. Now we have already found the formula for finding the volume. This volume is this particular limit. Now this is the exact volume where both m and n goes to infinity. But since here our m and n are finite and are equal to 2, this will no longer be an exact volume but an approximation. So the volume under Z is approximately equal to the double sum, where we start our I from 1, end at m, j from 1, end at n. We have our function ij star, yij star, delta A. Now we already know that delta A is just, it's equal to 1, right? So delta A is 1. Now let's evaluate this double sum. We know that both m and n are equal to 2. I starts from 1, j starts from 1. Now just simply write this function and the area down. We also keep delta A as it is. Now the rule of double sum is we do the inner one before the outer one. So let's do that. We keep the outer one as it is, I equals to 1 and n sub 2. Now for the inner one, the first term will have j equals to 1. So let's write that down. X does not, I just remains as I. So now j equals to 1. Of stars. This is the first term. Now we want to evaluate the second term. Now before we go to the second term, we must increase the value of j from 1 to 2. We increase the value of j by 1. So now we have x star, j is 2, y star. Delta A remains. Now we can apply the single summation for I equals to 1 to 2. So let's do that. The first term will have x star 1 1, y star 1 1, because I is 1. We're still not done with the first term. We still have this one to go. 1 2 1, 2, delta A. Now let's go to the second term where I increases by 1 from 1 and it's now at 2. So I is 2 now. So 2, 1, y, 2, 1 star delta A from here. So we have x 2, 2, y 2, 2 here because I is 2 here times delta A. Now before we find the star coordinates, we should label our regions in the form Rij, where I indicates how much we are towards the right and j indicates how much we are towards the left. And the first one, which is the R11, is always the lowest left corner. Here the lowest left corner is this particular region. So this is R11. Now we move 1 unit towards the right. This means our j value will stay the same because j value increases or decreases with y. Here we are only changing in x. So we have the j value of 1, but our I will increase by 1 because we are moving 1 unit towards the right. So this is R21. Similarly, this is from here we have increased y by 1, but x has stayed the same. So we have R2 as this one, and since y has increased by 1, so the y counter j will also increase by 1. Here we can see that you can go from one point to another point in this way. So there are lots of ways to fill up this region. You can choose any way you prefer. So I'll just go in a circular way. We have R22, right? So we now decrease our x value by 1. That means the first coordinate, which is I, will change from 2 to 1. It will decrease by 1. But y has stayed the same, right? There is no y change jumping from this box to this box. That means this is R12. These are my 4 regions. And if I want to find the star coordinates, what I have to do, if you remember from the previous video, that the xy star coordinates along the R11 box is just x11 and y11. And here, this is half and half. Right. This one. Right. So let's put that. So we have f of x star 11 is half, y star 11 is also half. Now delta A is 1. We have calculated it before. Here it is. Delta A is just 1. So we put that. Now let's find the 1, 2 region to find x1, 1, 2 star and y1, 2 star. So the 1, 2 region is this one, and x star 1, 2 is actually equal to half then, and y1, 2 star is what R1, 2 stars y coordinate is. This is 3 by 2. So this will be half, comma 3 by 2 along with multiplication of 1 due to delta A. Similarly, we can find the rest of them. So this is at the region R21. So let's go to R21. This is R21. Here we can say that the x coordinate of the x star coordinate must be 3 by 2 and the y star coordinate must be 1 by 2. So we write that down. Now delta is 1, which is why I've put product of 1. Similarly, the last one will be interested in the R22 region. Here is the R22 region. Here both coordinates, both x22 star and y22 star is 3 by 2. Here we just write down delta A. Now if we do this sum, we will get the now if we have to evaluate the function at each of these points, right? So if you do this using the elliptical paraboloid function, here z equals 16 minus x squared minus 2y squared. Now we just have to use z equals to f of xy, which is in fact equals to 16 minus x squared minus 2y squared. So if you want to evaluate what f half is, we put the value of half in the x coordinates, also this value here it's half in the y space. So it's here it should be 16 minus, I'm just going to show this one how to get this done, half square, and if you evaluate this, you'll get that this is 61 by 4. Now you just write down these values of this function. The first one is 61 by 4 times 1 plus 45 by 4 times 1. This is the 45 by 4 is the value of f12, 32 plus 53 by 4, the value of this part, plus we should have a times 1, (37 by 4), this one, f of 3 by 2, 3 by 2 times 1. And the value of this is exactly 49. And this means that our volume approximately equals to, under these conditions, is 49. Now we have the next part of the questions, which reads as follows. Now write down the approximate value of the double integral over the region R and 16 minus x squared minus 2y squared times dA. So we know that the double integral is the same thing as the volume. Therefore, this integral, the approximation of this integral is the same thing as the approximation of the volume. Right? And we know that the approximate volume is 49. This means that an estimation of this integral is also 49. So far, we have been looking at regions of integration where the region R was rectangular. Now, what if the region is not rectangular? We'll look at a few cases where the domain or the region of integration is not rectangular. Now, in order to identify these regions, we'll use either a single pair of inequalities or multiple pairs of inequalities. We'll also apply Fubinis theorem on two different circumstances. The first one is applying Fubinis theorem on type 1 regions. Now, what is type 1 region? Type 1 region is one where we identify all the pair of inequalities in a way that the first inequality that we take will satisfy only the y coordinates. The second one that we'll take will satisfy the x coordinates. Let's look at a graphical example. And here we have a region bounded by two functions, y equals to g sub 2x and y equals to g sub 1x. And let's call this region R. Now note that all the points in this region are bounded by these two functions. And in terms of inequalities, we can say that y must be in between g sub 1x and g sub 2x, which means that any point in this region is above or on the function g sub 1x, or it is below or on the function g sub 2x. For instance, a point over here does not lie on this region because its y coordinate is definitely above g sub 2x. And similarly, we'll look at the x coordinates now, which are quite simple because we have the x coordinates are not bounded by functions, they are bounded by constants. Excuse the bad drawing. So the x coordinate is definitely on this region. All of the x coordinates must be greater than or equal to a, because it's towards the right of a, and they must be less than or equal to b, because it's either on this line x equals to b or on the left of it, all of these points. So these two inequalities will tell us what region R is. This will give R. Great. Now let's say we have a function f of x comma y equal to z, and if we do this integration on this region R, we'll get this volume underneath the z or the surface and onto this region which is not rectangular, and this volume is the value of this particular integral. Now what does Fubinis theorem say on this circumstance, on this particular type 1 region? It says that if my function f of x comma y is continuous on my region R, or sometimes also called domain, if it's continuous, the function is continuous, like this surface, we can see that this particular surface is continuous on this particular region. This region is R, and if it's continuous, then we are allowed to write the integral f of x comma y dA as a combination of two integrals of one variable. For type 1 regions, we drew the y integral first and then the x integral, and the y limits are given by these inequalities, as y is always greater than g sub 1x and less than g sub 2x, and the x limits are from a to b, because x is always greater than or equal to a and less than or equal to b. Fubinis theorem also allows us to treat all the other variables as a constant while we're doing one integral. In this particular case, this means that while we're doing the y integral, we are allowed to treat x as a constant. And the notation that we'll use in this particular lecture series is that we'll always do the inner integral first. Like here, we have a double integral f of xy. The first integral that we'll do is with respect to y, and the second integral which we'll do will be with respect to x, because it's going from inner to outer. Whichever notation we use, the value of these integrals are almost always a number. Now we'll take a look at type 2 regions. Type 2 regions are those where we write the first inequality in terms of x and the second inequality in terms of y. So let's look at a graphical example to get an understanding. It's very similar to the type 1 regions in terms of logic, that all of these points have x coordinates which are larger than the greater than or equal to the x coordinates of this particular curve. The curve is h sub 1 y. So since the x coordinates are greater than or equal to this, and we all know that x increases as we move towards the right, that means the x coordinates within this region R is definitely either greater than or equal to, which means that it's lying on this particular curve. And we also know that all of these x coordinates must lie either to the left of this particular curve, which is h sub 2 y, or on this particular line, which is why we have written it as less than or equal. So this will uniquely define the x inequality, and similarly we can see that all of these particular coordinates have y coordinate value which must be greater than y equals to c. Right, that means the y coordinates are greater than or equal to, they can also lie on this line, it must be greater than or equal to c. So now all of these coordinates also satisfy that y is less than or equal to d. That if it's equal to d, it means it lies on this line. If it's less than, it means anywhere here. And these two inequalities will give me R. And any points which do not satisfy any of either of these inequalities, for instance, if we have a point over here, it does satisfy the y inequality, it is within y equals to c to y equals to d, but it fails to satisfy the x inequality because x is definitely larger than h2 here, it is more towards the right than h2. Now we are in a position to state Fubinis theorem applied on type 2 domains. And what Fubinis theorem says is that if our function f of x comma y is continuous on the domain, on the region or the domain. For instance, here we can say this is the type 2 domain, and on this region the surface z equals to f of x comma y surface is always continuous. This means that we can apply the Fubinis theorem, and then what we can do, the idea is very similar to Fubinis theorem on type 1 domains, like the double integral on a region R of f of x comma y times dA is equal to a combination of integrals of one variables. For type 2 domains, we do the x integral first and then the y integral, and we'll write down the y integral, the x limits for over here. So we know that x is bounded by this inequality. So just like the example for type 2 domains, it should be h sub 1 y and h sub 2 y as the upper limit, and the lower limit of y is c because y is in between c to d, so the lower limit is c and the upper limit is d. I will take a look at this special case, which is for rectangular regions. Now here we can use the same pair of inequalities for both type 1 and type 2 domains. Sorry. For instance, this is a rectangular domain, right? Because, and here we can state this region in terms of both type 1 and type 2. In type 1, what we do is we do the y inequality first. So we know that y is bounded between c to d, and x is bounded between a to b, because all the x coordinates lie in between a to b in this region. Similarly, for type 2 integrals, first we give the x inequality. We know that all of these points lie between x equals to a, from x equals to a and then till x equals to b, that means a to b. Similarly, then afterwards we will do the y inequality, and y is bounded between y equals to c to y equals to d. Now interestingly, note that both of these pairs have the exact same inequalities, just one is after the other in this case. This is only true for rectangular domains. And therefore Fubinis theorem, we can use the type 1 Fubinis theorem that we've learned a bit earlier, that the double integral of f of x comma y times dA is equal to the combination of one variable integrations of f of x comma y, where we do the y limit first for type 1 and then x limit, and we know that the y limit is from c to d, and the x limit is from a to b here. And this is let's just write type 1. For type 2, Fubinis theorem will allow us to write that the double integral of f of x over the region R can be written as a combination of integrals of one variable, where we'll do the x integral first and then the y integral, and the x limits are given in this inequalities from a to b, and the y limits are from c to d. And since both of these are the same double integrals, as you can see, these are exactly equal. This one is equal to this one. This means that these two must also be equal. So in the rectangular, for rectangular domains, we have the special relationships, that the integral, if we do the x integral first, the y integral first and then the x integral, we'll get the exactly same result as if we do the x integral first, this one, and then the y integral. The x integral first and then the y integral. Now let's discuss the intuitive reasoning behind Fubinis theorem. Here we'll discuss the case for rectangular domains. Let's say we have a solid C for some function z equals to f of x comma y, which is the surface, which is this particular surface, and C is this solid, this entire solid, and we take a cross section anywhere within our limit of within our interest. As it's a rectangular case, x is lying in between a to b, and y is also lying from c to d, I think, although it's not necessary for understanding the intuitive reasoning. So we take this slice of solid and we call the area of solid a of x. We can see that the area must change, as if we start from x equals to a, the area is smaller for this diagram. As we go towards a, x equals to a, that means we decrease x. Decreasing x will increase the area of the cross section here. And what we want to do is find the volume of a small volume from starting from a of x. So let's draw out this a of x as a cross-sectional slice, and we take a very small, infinitesimally small height, and we this infinitesimally small height is in the same direction as x, right? So we have increased our x value by a very small amount. That means this is nothing but dx. And this infinitesimally small volume must be equal to this the infinitesimally small volume. So if V denotes volume, the infinitesimally small volume is dV, is equal to the base area. The base area over here is a of x times the infinitesimally height, which is dx. And if I integrate both sides, now I'll get, this will give me volume, or simply V. Let's put this out. V, which will be equal to the integral of a of x dx. Now just note that because the height has increased by a really small amount, an infinitesimal small amount, the area of both of these cross sections barely change. That's why we can calculate the volume, calculate the infinitesimal volume in this way. So now we find that v is the integral of the area function with respect to x. Now how can we find a of x? Now in order to find a of x, what we'll do is, as we are trying to find the area, let's focus on this particular cross section, this red cross section. All the points on this cross section have the same x value. Here you can see that x is not changing as we're for every point on this slice. However, y changes. As y changes in this direction, we can move in this direction on this slice. Also z changes in this direction. As we go up vertically, our z value will increase. However, x always stays the same, and this is exactly what we'll use. And here you can see, as we know, z is equal to f of x comma y, but we've seen that f only depends on y, right? So the function, as long as we're focused on the slice, only the y coordinates change, x does not change, which means z depends only on y. So we can, for this slice only, we can rename this function as it depends on y, and we call that g of y for the slice, only. Okay, and so let's plot the value, the graph of z with respect to y. So this is actually z equals to g of y as a function of y. We can see this is a two-dimensional graph. It depends on, z depends only on y, not multivariable. And here y varies from c to d, as in the diagram. Here c is covered due to this solid. However, we can d should be here, as it's a rectangular domain. So the area is just the area function, right? So, but the area function is in fact the integral, the definite integral from c to d of z with respect to y, and this will be equal to, since z is g of y dy, on this slice x, z does not depend on x, and g of y on this slice is also equal to f of x comma y. dy. Now the double integral is the volume, right? So we're calling it v here. Now what is the volume? The volume is, I forgot to mention the limits. It should be the x limits from a to b. The volume is the integral from definite integral from a to b of a of x dx. So we'll just write that down. Volume, definite integral from a to b, a of x dx. However, a of x is in fact equal to c, the definite integral from c to d of x comma y dy, and we still have, this is just a, and we have then dx. This is in fact like Fubinis theorem for type 1 domains, because we are doing the y integral first. Now a similar argument will show you that if we keep y as a constant on a particular slice where we change x and z, you can show with the exact same reasoning that the double integral is also equal to this particular integral where we do the x integral first and then the y integral. This is type 2. This is a type 2 way of doing this integral. And now we will do a problem. The problem is as follows. We have given the same z function as we have done the first problem in this video, where we have the function 16 minus x squared minus 2y squared on the same domain R with x interval from 0 to 2, and then 0 to y also from changes from 0 to 2. Now what we have been asked to do is, using type 1, find the a double integral of f of x with respect to the area. So since it's a type 1, our function, let's write down the function 16 minus x squared minus 2y squared. Type 1 means we do the y integration first and then the x integration. And the y limits are from 0 to 2 due to this, and the x limits are also from 0 to 2 due to this. So we'll do the y integral first, as this is the type 1 region, and we can use Fubinis theorem while we are doing the y integral, which is equivalent to saying like we're treating x as a constant. So if we do the y integral, we'll get 16y minus x squared y, x is being treated as a constant, minus 2 by 3 2/3 of y cubed, and dx, the outer integral, the x integral remains as it is, and this is nothing but, we also have to take the limits. Yeah, so once we simplify the limits, this is 16 times 2, which should be 32, minus y is 2, right? So it's minus 2x squared. X is as it is, x is being kept as it is, and y cubed is, we'll have to substitute 2 here, so 2 cubed is 8, 8 times 2 is 16, 16 by 3, and for all three terms become 0 because 16 into 0 or x squared into 0 or 2/3 into 0 cubed is all 0, so we have to subtract this with 0, the lower limit, when we use the lower limit, and then we have to do the integration with respect to x. Now we should simplify this a little bit because both of these are constants. This is 80 by 3, 32 minus 16 by 3 is 80 by 3, minus 2x squared dx, and this is just 80 by 3 x minus 2/3 x cubed, where we take the limit from 0 to 2. So this will be, as we substitute 2 here, and this will be 80 times 2, 160, divided by 3, minus 2 cubed is 8, 8 into is 16, 16 by 3. So let's calculate that out. This is exactly equal to 48. And if you remember that at the very first part of the video, we found that the volume or the integral using midpoint approximation, that it was approximately equal to 49. See that these two values are very close to each other.